In this video, we're going to take a deeper look at just ionic bonding. At this point, you should already be able to describe ionic bonds and identify them. But at the end of the video, you should be able to calculate and describe the lattice energy that keeps the bonds together and calculate ionic bond energies of formation. So the question of the video is, are all ionic compounds created equal? So we're going to come back to the slide later and see if we can have a hierarchical list of what ionic bonds might be the strongest. So first, in order to do that, we have to look at the ionic radius review, knowing that positive ions, when they form, are generally smaller than the atom because they lost their electrons, and you can see that for all the red ones that are positive, and that anions are usually larger because they gain electrons, and so the same number of protons can't pull on the new electrons as strongly, and so you can see all the ion part, the blue part, being larger. So this is something we really should make sure we know. But generally, overall, we still have that increase down a group and a decrease in size across the table. So if you consider O2 minus, F minus, Na plus, Mg plus 2, and Al plus 3, they're isoelectronic because they have the same number of electrons, which means they have the same shells, but they're not the same size. They decrease respectively because as you go across those atoms, they get more and more protons pulling on the same number of electrons. Remember, we talked about this in a previous video. So if we were going to be needing another example, these four elements are also all isoelectronic, but the one that has the most number of electrons, like selenium, is going to be pretty large, and the one with the most amount of protons is going to be really small, and the one that's the least amount of protons is going to be really big. So I kind of reorganized them and shuffled them from to make the size increase as we go across. It's important for something called lattice energy. So let's just talk about one particular ionic compound, lithium fluoride, that should form naturally because lithium should want to lose its valence electron, fluorine should want to gain an electron, and therefore it should be a perfect, nice plus-minus pair. And therefore, we consider the heat should be exothermic, stable, and release its energy as a negative value. So let's look at what happens when lithium fluoride forms. The lithium and the fluorine have to become ions. So if you remember from the previous videos, when lithium forms its ion and loses its electron, we call it an ionization energy. And if we use a textbook and look it up, the ionization energy requires 520 kilojoules. Fluorine attains electrons. That's called electron affinity, or its ability to attain electrons. And when it attains electrons, it actually gives off 328 kilojoules, which is actually good, stable. But if you sum only these two parts together, you're going to get a value that's still positive, and that is not stable in the world of heat, right? So that means that something else must be in play in order for this reaction to occur. There must be other things going on. So one of those things is what we're saying is called lattice energy. You should write this down, it's in red. Lattice energy is a change in energy that takes place when separate gaseous ions are packed together to form an ionic solid. Key words here is separate gaseous ions, so we have to have them be gases to pack together as an ionic solid. So there's phase changes going on, and there's this lattice energy that takes an ion into a solid phase. And so the lattice energy is generally exothermic to take care of all the positive work that we need to do to make the compound. So let's get a little deeper in lattice energy. Lattice energy goes back to Coulomb's law. We used to use it to describe how a proton attracts an electron and how close they are would attract better. But now we're going to do it in terms of charge of an ion, so like a little bit larger of a scale, right? The higher the charges are, the better that they're going to attract each other. So compounds that have ions like +3 and -3 will have larger lattice energies because they're going to attract better than if something that is only plus and -1. Also, we have to talk about the radius. Remember the size on the bottom? The closer they are, the better their attraction will be. So if they have a smaller ionic radius, which is why we went over that, they'll be closer, so the protons of one element will attract the electrons of the other element better. If they're further away, like they have larger ionic radii, then the protons are further from the other element's electrons and they won't attract as well. So what would happen to the lattice energy if the radius was tripled? If there is a really large radius, they're going to attract even less, so if energy will decrease. Or if the charges were doubled, so if you have twice as much charge, they'll attract twice as much, right? And what if the radius is halved? If the radius halves, that means they're going to get closer, so the lattice energy will double. So let's do some comparisons. Which one will have a more exothermic lattice energy? So if we look between sodium chloride and potassium chloride, I'm going to say sodium is much smaller atom, so it can huddle up closer to the chlorine and make it a stronger bond. Between MgCl2 and LiF, I would pick MgCl2 because MgCl2 has a +2 charge attracting a -1 charge. So that higher charges will be more attractive than lithium fluoride that's only +-. In the third example of lithium fluoride versus LiCl, they both have lithium, but fluorine is going to be a smaller atom or ion, and so it's going to be able to get closer to lithium's protons, making a stronger bond. In MgOH2 versus MgO, MgOH2 has a +2 -1 charge versus MgO +2 -2. They're transferring more electrons, but makes it a stronger bond in MgO. In our last example, NaCl versus Na2O, again, oxygen's a -2 charge. It's transferring 2 electrons, which makes it a little bit stronger than the only transfer of 1 electron in NaCl. So look for those charges in small radius. Remember we had that question in the video? Maybe pause it now and see if you could do it on your own. All right, let's check your work. In MgSe versus MgS, I think MgS would win because S is slightly smaller than Se, so its electrons can be attracted to Mg's protons better. In KCl versus Ki, I picked KCl. Again, Cl being smaller than iodide ions, and in that case can get closer to the K, creating a stronger bond. LiF, because both of them are smaller than Cs and Br. And SRO, different reason though. SRO has a higher charge, so charge trumps size, right? Charge is more important because it's transferring more electrons. Now we only have 4. Let's see who we can get here. For MgS versus KCl, I picked MgS because it has a higher charge ratio. And in LiF versus SRO, again, I picked SRO because it has a higher charge ratio. In our last example, MgS versus SRO, it's a little tricky because they're both charges +2 -2, which means they're both trading 2 electrons. Now it comes down to size. Mg is significantly smaller than Sr because it's significantly less energy levels. O is slightly less than O because it only has 1 energy level off. So in that case, I'm picking MgS as the winner because it has the most charges with the smallest radii. Now let's put it all together. To form an ionic substance, we need 5 things. Ionization energy to make the ion, electron affinity to make the negative ion, lattice energy that we just practiced, but also some other factors. We need to make them all gases and singular. So the lattice energy requires them to be gaseous, singular substances, and so for sublimation might also be necessary. And like we said, some elements like fluorine are diatomic or oxygen, and so we have to dissociate them and break them apart so they're singular gaseous ions. And so the general steps must be taken. The sublime anything that is a solid, ionize anything that needs to become positive, dissociate any bonds that need to be broken, affinity of electrons to get them to be negative, and then the lattice energy can bring those positive and negative ions together as a solid. So this is what it might look like. If I wanted lithium to react with fluorine to make lithium fluoride, notice it says a half fluorine because we're looking at it 1 particle to 1 particle, but there's going to be only one of those fluorines in the fluorine bond reacting to make LiF. This is how we can balance it, right? First, lithium will have to sublime. I looked up the value in the reference table. It takes about 161 kilojoules to sublime. That is not very good. Like stability-wise, we need to put energy in to do that. Similarly, it takes energy to ionize that lithium as well. So lithium is kind of resisting this change in a way. So the ionization is removing its electron. But actually, it's ready to bond now, lithium ion gas. Fluorine has a bond between it. So we have to break that bond, and that's a bond energy of 154, but we're only breaking half the amount of bonds in moles because of the half coefficient here. And electron affinity is that 1 fluorine atom has to gain electrons to form an ion. Finally, something that's negative though, right? Negatives show stability, that it can release its energy on its own. So altogether, if we didn't look at lattice energy, we would have a very positive reaction, which would imply that reaction doesn't work. But the lattice energy takes the lithium ion and the fluorine ion and forms a lithium fluoride solid, which is what we wanted. Actually, if you look through all these equations, everything should cancel but the original. So the lithium gas will cancel with lithium gas, the lithium ion with lithium ion, electron with electron, fluorine gas with fluorine gas, fluoride ion with fluoride ion. Notice the only ones that don't cancel are the original equation, and that's kind of how you know you have it right. If everything cancels, then you can actually sum all your heats. And now that we sum all our heats, we get a negative heat value, which means it is stable. Again, you need to know that positive reactions are less stable than negative ones. And so since the values in your textbooks, all these values are in the appendix of your textbook, and notice so all this overall sign is negative and therefore favorable, Also that the dissociation, like I said, had to be halved because of this coefficient here. At this point, you should be able to identify and describe ionic bonds, calculate and describe lattice energies, and calculate ionic bonds of formation.